Thank you very much, everyone, for joining this edition of the Liftoff webinar series brought to you by Lyft here in Detroit. My name is Joe Steele. I'm the Communications Director here. We are happy to have Dr. Fan Zhang with us today, talking about the accelerated design of metal alloys by high throughput calculation using CALPHAD simulation tools. So we will get to her presentation in just a minute or two, but I wanted to share a little bit of information for those of you who don't know about Lyft and what we are and who we are and what we do. But I would like to do a little bit of housekeeping before we begin. If I can ask everyone to put their phones on mute, I would certainly appreciate that. We are recording this presentation, so it'll be posted on the Lyft website later on. So we want to limit the background noise as much as possible. There is a chat function. I'm going to send everyone a message here, but if you want to address any questions using the chat function, you can see it on the menu, I think, towards the top of your screen, or I'm going to send everyone a chat right now. You can ask any questions there, and I'll facilitate the Q&A as we get to the end of the presentation towards the 1 o'clock hour here Eastern time. So look forward to that. So at Lyft, our mission is simple. We are here to advance technology and talent development and drive rapid implementation of smart manufacturing. And we have a vision of driving American manufacturing into the future. We were born in 2014 here in Detroit. Our initial focus in those first 5 years has been materials and materials research, mostly on the metals side of things. And we are, as we evolve and grow, we're looking towards again, rapid implementation of smarter manufacturing to help small and medium-sized companies specifically drive towards the future of that connected smart manufacturing future involving materials plus process plus digital. We're looking forward to doing that, and hopefully you guys will stay close to us as we evolve into that future. We really are here to bridge the gap between the investments that's made early on, the investment and research that's done in government and in universities, and the private sector. I'm sure many of you have heard about the valley of death that exists between those two, where the funding dips between the research that's done early on and at the private sector when a innovation is ready to hit the marketplace. So our goal really is to connect those two. Operate in that technology or manufacturing readiness level 4 through 7, where that valley of death exists, and really connect those research opportunities. We are part of a larger network. We are one of 14 Manufacturing USA institutes around the country. As you can see on the map here, we are located here in Detroit with our focus on lightweight materials. But you can see around the gamut, around the country, it really runs the gamut between different technologies, from flexible hybrid electronics out in California to additive manufacturing down in Ohio to advanced robotics in Pittsburgh, and wideband semiconductors over in North Carolina. Some of these institutes are sponsored by the Department of Defense. That is where Lyft is. Our main funder is the Department of Defense. There are 8 institutes that are funded by the DoD. There are 5 institutes that are funded by the Department of Energy, and there's 1 institute that is sponsored by the Department of Commerce. You can learn more about all of the other institutes either on the Lyft website at lyft.technology or at manufacturingusa.com. A few highlights from what Lyft has accomplished and done and impacted over the first 5 years. We have over 200 industry research and academic and workforce development partners around the country. At any given time, we have had 600 or so engineers, researchers, professors, economic developers working on Lyft-supported initiatives. Our Lyft facility here in Detroit really has an open door policy. We accept visitors all the time to show them what we're doing, and we've had over 3,000 visitors in the last 12 months. Our work has impacted over 350,000 students and teachers through 40 education workforce development initiatives around the country. We've invested $78 million in technology projects. We are here in Detroit in a 100,000 square foot facility that we share with IACME, one of the other Manufacturing US institutes that you may have seen on the map previous slide, we have $20 million worth of equipment on the lift side. So we are very proud of our facility here and the work that we've done. So I encourage you to come visit us next time you are in the Detroit area, or make a special visit to come check us out and see what we're up to. Just a peek at some of our members. We run the gamut from large companies to small startup companies. You can see the government partners that we work with, both on the funding level at the top with the Office of Naval Research, the Department of Defense, and the Michigan Economic Development Corporation, as well as some of the research labs you see at on the bottom: Air Force Research Lab and Army Research Lab and NASA, and some of the other groups. You can see we work with universities around the country as well. But again, you can learn more about LIFT at lift.technology. You can follow us on our social media handles, which I encourage you to do so. On Twitter, we are at News from Lift, and on LinkedIn, you can follow us there. Just search for Lift-Lightweight Innovations for Tomorrow. Some of the services we provide, you can see on the screen. We got various levels of membership. We are a membership-based organization. So we encourage you to take a look at some of those, or reach out to us, and we'd be able to talk to you through some of those as well. Some of the government R&D programs we can connect you with, and some of the education workforce development products and services we have, as well as the other engineering type of services that we provide as well. So we'll look forward to hearing from you, but I know you didn't come here to hear from me. You came here to learn from CompuTherm. So at this point, I'm going to turn the presentation over to our speaker, Dr. Fan Zhang from CompuTherm LLC, and you can take it away from here.
All right. So I request control. Let me see if I can. Okay. No. Okay, it's working. All right. Thank you, Jill, for the introduction and give me this opportunity to talk about our work at CompuTherm. And I would like to thank you all who take the time to join this webinar. The title of my presentation today is Accelerated Design of Metal Alloys by High Throughput Calculation using CALPHAD Simulation Tools. As you can tell, I use a smaller font for high throughput calculation because that's only part of my presentation today. So a few words about CompuTherm. CompuTherm is a spin-off company from University of Wisconsin-Madison. It was founded by Professor Austin Chen in 1996. And our passion is basically develop intelligent, reliable, user-friendly software based on the CALPHAD approach. So we also work a lot of government projects. We collaborate with industry partners and universities, and so we work on challenging programs with potential payoff. We located in Madison, Wisconsin, so if you have any thing you are interested in CALPHAD calculation, and if you would like to visit us, you're welcome. But I would suggest you come during the summertime. Okay. Doesn't work again. Okay. So summer is very nice here at Madison. Beautiful blue sky, and we have lakes here. But if you like snow, you can come winter time. Okay, that's how you will expect during the winter time. We got a lot of snow. Okay, so if you it's not. So the outline of my presentation is the following part. First, I would like to give a brief introduction about CALPHAD approach, and then I'll talk about the simulation tools developed by this approach. I will then show some fundamental features of PanPhase software, and then I'll talk about high throughput calculation for alloy design. I will also touch a little bit about how we use CALPHAD approach to study oxidation and corrosion resistance. Then the summary. So a little bit about CALPHAD approach. if you Google the definition of CALPHAD, so this is what you will find from Wikipedia definition. And basically it tells you Professor Larry Kaufman initiated this idea about 60 years ago. And right now, actually, it has become a very important building block for SEME and MGI. As the name stands, CALPHAD, the initial idea of this CALPHAD is for calculation of phase diagram. Even though its approach has gone a long way now, it can do a lot of more than that. Then the next question you may ask is why phase diagrams? Well, phase diagrams are the beginning of wisdom, not the end of it. This is the famous quotation by William Hume Rotary. If you do not know this famous person, if you are a TMS member, you know this is a very most prestigious award from TMS. Which honors those who made significant contributions in the field of material science and metallurgy. Then now you say, okay, I agree phase diagrams are very important for materials design. However, I can find a lot of phase diagrams from handbooks. So what's the big deal about CALPHAD approach? Well, from handbook, you get the phase diagram. That's what you get, right? For example, this is aluminum nickel binary phase diagram. You get this binary phase diagram, and if you want to know, okay, now I want to add a little bit cobalt or chromium, how the phase relationship will change. Well, you do not get anything from this binary phase diagram, right? Well, this is the advantage of CALPHAD approach. Basically, we can calculate multi-component phase diagrams, and it's live phase diagram. You can basically get a lot of information from the calculation, not only limited to phase diagram. You can also get a lot of thermodynamic properties and things like that. And this is very important for modern materials design, because modern materials are mostly based on multi-component system, right? Okay, so here is just, I want to use one slide to summarize the philosophy of the CALPHAD approach. So this approach is basically use available experimental information and theoretically calculated data to obtain self-consistent Gibbs energy functions of phases in the system. We call this procedure as build a thermodynamic database. And then the purpose is really to predict stable and metastable phase equilibrium and thermodynamic properties in the composition regions where experimental data are not available, especially for multi-component system. So I wouldn't say CALPHAD approach is a machine learning approach, but if you compare these two approaches, they based on similar idea. Basically, we use the available experimental data to build models and the model parameters, and then we use the models to predict some information that we don't get from experiments, right? Okay, so let's use a quaternary system as an example. You probably will not find any phase diagrams for this quaternary system in any handbooks. However, we know this quaternary system is built up by 4 ternary systems, and then each ternary consists of 3 binaries. So this 4 ternary share of the binary system. So in this quaternary system, we have six binaries and 4. So the idea is to use available phase diagram and thermodynamic property data of the binary system and also some of the data from ternary system to build up a database. I mean the models and the model parameters for this quaternary system. Then we can predict the phase equilibrium in this quaternary system. So based on this idea, we can build up a multi-component database so we can predict the phase equilibrium information in multi-component system. So that's basically the idea of CALPHAD approach, right? But now, okay, I just talk about how to build up a multi-component database which provide reliable models and the model parameters for the simulation. But that's only one of the essentials of the CALPHAD approach. Just like you are cooking a meal, okay? Ingredient alone does not make a good meal, right? So you also need a cookware. So that's why we need a good software to perform the calculations. So basically, two essentials for the CALPHAD approach is one is database, the other one is software, okay? So if you search the software from internet, you can find a list of software from different companies like Thermocalc and OpenCALPHAD, which is also very popular right now, and a few other software. PanDAT software was developed by CompuTherm, and we started to develop this software in 1996, as I said, the company started. And the first of PanDAT software, first version of PanDAT software was available in the year 2000. And that at that time, the software is really focused on phase diagram calculation. But now this software has become like an integrated platform for simulations, not only for phase diagrams, but also we can do like precipitation simulation and diffusion simulation and so on. Okay, so next, before I talk about high throughput calculation, I want to give an overview about the fundamental features of PanDAT software. It's going to be very brief because I don't have much time to talk about it, but I think it's good to know some fundamental features of the software. So here I list some of the categories for the calculation, like point calculation, line calculation, section calculation, and so on. So the idea is mostly to calculate phase equilibrium and also thermodynamic related information in the multi-component system and this under different calculation conditions. 2D diagram, the most typical 2D diagram is like a binary phase diagram. For example, here I shows aluminum magnesium binary phase diagram. However, if you want to know some details, like if you have an alloy, you want to know how this alloy goes through phase transformation and phase fraction change, when temperature change, then you can do a line calculation, like as the one shown in the lab figure. You have a fixed composition and you can do a line calculation at different temperature. Certainly, you can also fix the temperature and you vary the composition, right? And I also want to mention that this line calculation is not limited to binaries, right? You can do the simulation in the multi-component system. And in a ternary system, well, actually a complete ternary phase diagram is in a triangular prism. But however, if you want to view the entire ternary phase diagram in the triangular prism, for the complicated ternary system, it's not easy to visualize. So that's why most of the time we calculate isothermal section and the isoplazo section to visualize the ternary phase diagrams. In this slides, we can see a 3D diagram. Usually we can only visualize some simple system, but very useful phase diagram is called the liquidus projection, which is the projection of the liquidus surface to a plane. Okay, liquidus projection is very useful to understand solidification process. For example, if you have liquidus projection, in this case a magnesium corner, then you have an alloy and you perform like a solidification simulation, and you combine the solidification simulation with the liquidus projection, then you can see the solidification path and then predict what microstructure you can get for this alloy during casting procedure. So this calculation is based on shell model, okay? So another unique feature from PanPhase software is contour diagram. So in this case, I will just use one example to demonstrate how we can use some of the contour diagram to understand for alloy design, okay? So this is an isoplast of titanium alumina side with some 4% of vanadium and a little bit of nitrogen and oxygen. So this isoplast is can be used to understand titanium alloy at titanium rich corner. For example, Ti64 alloy, right? And this is titanium. This alloy is in the alpha beta region, for example. However, this alpha beta region is a large region, vary with composition and temperature. It's not obvious how much of alpha and beta you can get if you have a composition and temperature. However, if we plot this phase fraction contours on this diagram, then we can immediately see what's the fraction of alpha and beta at each composition and temperature. So this information is very useful for alloy design. Then you can select the alloy composition and heat treatment temperature to achieve a certain fraction of alpha phase and beta phase in the microstructure, right? And another example is like titanium alumina alloy design. So the main feature of titanium alumina is it's lightweight, and the composition is in the middle of titanium alumina is basically around 50% of titanium and 50% of alumina. However, niobium is one of the important addition to titanium alumina. The question is, in order to reach certain properties, and also we want to keep the alloy light, how much niobium we can add? We do not know from this phase diagram only. However, if we put the density contour lines on this phase diagram, we can immediately tell how much niobium we can get to maintain the density of this titanium alumina at certain stage, right? So this is also very useful information for alloy design. And we can certainly plot all kinds of contours of physical properties on the phase diagram. So all this information is useful to help user to design their alloy that meet both phase stability and also the properties. That was the major concern, right? All right. So that's basically some features of PanPhase diagram module. As you know, for alloy design, first we need to consider, we want to choose the right composition, right? So the microstructure will contain the right phases and the phase amount. And also we have concern like melting temperature and density and so on. So that's all related to the right composition. But on the other hand, we also need to choose the right processing conditions. For example, homogenization temperature, the cooling rate, aging temperature, and so on. So we can develop the alloy with right microstructure and balanced properties. So it has good performance, right? And so with PanPhase software, the phase diagram module is mostly focused on the right composition. So it helps user to design the alloy with right composition. And we have developed another two modules like Precipitation Module and Diffusion Module that can be used to perform kinetic simulations, so that helps user to design the processing conditions. Okay, so in the next few slides, I just want to quickly go through some of the features of precipitation module and diffusion module. So precipitation module is designed to simulate temporary evolution of average size, particle size, number density, particle distributions, volume fraction, and so on. And we can also consider the co-precipitate, post-precipitation, if you have two precipitates, like, for example, nickel 718, we have gamma prime and gamma double prime. Then we can simulate the co-precipitation of the gamma prime and gamma double prime. We can use the module to estimate like the interfacial energy, and we can consider heterogeneous nucleation. We can also consider different morphology evolution. It's not limited to spherical, okay? And we, the new version of 2019, we also include some strength model for nickel-based superalloys. I'll give you a quick example. This is the simulation for alumina alloy 7000 series, and this slide shows the particle evolution, size evolution, and the yield strength evolution with time when the heat treatment condition is H at 160 degrees C for 1000 hours. Okay, so with this precipitation module, basically we can perform some virtual experiments, right? So we try different heat treatment temperatures, different cooling rate, so we can play with it to see what's the best heat treatment condition, so for you to obtain the microstructure you like. So this is very important to optimize the heat treatment condition. This is just an example of gamma prime and gamma double prime co-precipitates in nickel-based superalloy. So this is a typical heat treatment condition, and then we can use this treatment condition to simulate how these two precipitate compete with each other to evolve during the different stage. Okay. So you can see the volume fraction, the particle size evolution, and also the particle size distribution, right? Pan diffusion module is a new module. It was released last year, but we continue to improve it for the new version. So 2019 version is better, and then the 2020 version will come early next year. Will be including models, okay? So it is used to like simulate a concentration profile of diffusion couples. It doesn't have to be couple, it can be sandwich. And also like a carbonization, we can simulate particle dissolution, homogenization, and so on. Okay, so this is an example like diffusion couple. It's a multi-component system. The left side is iron 100, and the right side is Inconel 718. So both nickel-based superalloy of multi-component system. So as you can see, we can simulate diffusion between multi-component diffusion couple. And I think the particle dissolution is one of the important applications for diffusion simulation, because basically we can calculate how the particles formed during solidification, how they dissolve during the homogenization treatment. So you can optimize the homogenization temperature and time, so you can dissolve these particles quickly and also save energy, right? So because of the time constraint, I don't have time to talk all the details, examples on the simulations. So that's basically give you some taste about these basic features of PanPhase software. So the next part I want to really spend a little bit more time is high throughput calculation. for alloy design. Okay. So the idea of high throughput calculation is to perform thousands of calculations altogether at user-defined compositions in the multi-dimensional composition space. And then after the calculation, we can do like data mining of the simulated results and identify the alloy compositions that meet users' requirements. Okay, so the purpose is really to accelerate alloy design by alloy development by design. Okay, so here basically shows the steps for high throughput calculation. The first step is user need to define the compositions, right? What you want to calculate, right? So in this case, I just gave an example to list a bunch of elements in there. And for each element, we need to give a starting composition and the end composition, and the number of steps you want to do the calculation. So, and then the second step, use the software just make the combination of all these settings and perform the calculation for thousands of compositions. And then after the calculation, step number 3, user will define the search criteria. What properties you have a major concern? Okay, what properties you're looking for? And then the step number 4, user will perform data mining and for the simulated results to identify the alloy compositions for the user. All right. And then number 5, the software will present the search results either as a table. It just lists all the compositions for the user. Okay, tell the user, okay, that's the compositions you're looking for based on your criteria for the properties. And then the other way is to show some of the color maps, like 2D color maps. Okay. Next, I will show you a few examples of use high throughput calculation for alloy design. The first example is to search high entropy alloys in this alumina, chromium, iron, manganese, titanium 5-component system. And the user-defined composition space. It is a 5-component, and each component, the composition vary from 0 to 50%, and each element with 5% step size. And the total number of compositions for this defined is 3,246 compositions. Okay, so we perform high throughput calculation for all the compositions. And then after that, user will define the screening criteria. For example, the criteria number 1 is the melting temperature should be higher than 1250. And also the first solidified phase is BCC phase. Basically, BCC phase is the matrix phase, okay? And then the second criteria is at 0.8% of the melting temperature, we want to have 2 phases, the matrix phase, BCC, and plus some of the precipitate phase, R21. And the precipitate phase should be smaller than 50%, right? And the third criteria is we want to keep this 2-phase structure stable until 50% of the melting temperature, okay? So from this criteria, we data mining the simulated results, and we found that number of alloys meet criteria number 1, we have 1,168 alloys. And for alloy composition that meet number 1 and number 2, we have 44 alloys. And for alloy composition that meet all the requirements, all 3 requirements, we have 8 alloys only. So as you can see, we down select from like total 3,200 alloys to 8 alloys for experiments, okay, for experimental validation, right? So this work is collaborated with Professor Liao's group at University of Tennessee. So they perform some comparison test, and they do find a couple of alloys, not one, okay, at least 2 or 3 of the alloys from these 8 alloys, and they have very good properties. For example, this one shows one of the example. As you can see, we compare the yield strengths of this newly found alloy, high entropy alloy, and compare with 4 other alloys. And some of them are commercial alloys. So as you can see, at low temperature, this alloy has the best yield strength, very high yield strength. But at high temperature, it is not as good as Inconel 718. However, this alloy has a much low density than 718. So this example demonstrates really the alloy design idea. So we can use high throughput calculation to screen wider composition space, and then we can down select a few potential alloy compositions for experiments. So it's really accelerate the design by a lot, significantly, right? Okay, so the second example is to search compositions with high potentials to form bulk metallic glass. Actually, this work, we did some work about 10 years ago to use phase diagram calculation 8 to 8, searching the compositions for bulk metallic glasses. And then we found that most of the composition that has high potential to form bulk metallic glass is at the low lying liquidus temperature. So at that time, we are able to find some of the compositions that form bulk metallic glasses, and the prediction were quite successful. However, this type of simulation is not so easy. If you are not the expert of CALPHAD approach, you do not know which sections you should perform the simulation. So it's not easy for everyone to identify the composition that has the potential. Recently, we revisit this bulk metallic glass prediction, and we use high throughput calculation to for this application. So here, what I showed is in this ternary system, aluminum copper zirconium ternary system, and then we calculate the liquidus temperature for several hundred of alloy composition, and then we present the simulated results as a color map of liquidus projection, liquidus temperature. As you can see, those solid points are the compositions that already identified as a composition to form bulk metallic glass by experiments. As you can see, they all located in the low liquidus temperature, okay, region, okay? And we can also plot another color map, which is the solidification range, which seems like the solidification range is also a good indicator for BMG formation. Okay, so we perform some simulation for some other ternaries and higher order system, and that seems like high throughput calculation are giving you really a good indicator, like to search the bulk metallic glass compositions. Okay. Okay. Now I have a third example. This example is used to predict crack susceptibility during solidification. So in 2017, Liu and Co. They published a paper in Active Material, and they have an index. Basically, they propose an index which can be used to estimate the crack possibility for different alloy composition in alumina alloy. However, if we do not use, if we have this index alone and we evaluate alloy then we can do like, certainly we can do alloy by alloy, right? We give an alloy composition and we use this index to evaluate its crack susceptibility. I don't want to go all the detail about how this index was developed, but here I want to show we can use high throughput calculation to develop cracking map. Okay, so in these 4 figures shown in this slide, the bottom right figure is experimental data. So basically, the area by the orange color 12, that's the area that's the most vulnerable to cracking during solidification. Okay, but if you can take a look of figure 1, which is the top left figure, that's the simulation we did using a cells model. So in this model, we do not consider back diffusion, okay? And as you can see, this map of the cracking region, the orange region, is kind of off from the experimental data, okay? However, if we consider the back diffusion, for example, the figure B and C, both consider back diffusion, but with different cooling rate. However, both of them predict the red area, okay, the composition area that are most vulnerable for cracking during solidification. So the take-home message for this simulation is, is basically high throughput calculation is very useful to develop a cracking susceptibility map. And also for the solidification simulation, considering back diffusion provides more sensible prediction for the cracking capability, the susceptibility, okay? All right, so I just used 3 examples to demonstrate how we can use high throughput calculation for alloy design. In the next few minutes, I would want to talk a little bit more about the application of CALPHAD simulation tools. So that's application to oxidation and corrosion, okay? The first example is sodium sulfate induced hot corrosion, okay? As we know, hot corrosion occurs in marine gas turbine engine due to the rapid degradation of high temperature alloy component. When it is exposed to sodium sulfate containing deposit and also with SO3 gas environment. We know that sodium sulfate is not molten at intermediate temperature, such as 650 to 750, which is mostly the application temperature. But when sodium sulfate forms solid solution with other metal sulfate, the melting temperature can decrease quickly, okay? For example, this diagram shows cobalt sulfate with sodium sulfate, this pseudo-binary system. As you can see, the melting temperature for pure sodium sulfate is 884 degrees C. When it forms solid solution with cobalt sulfate, the melting temperature follow this purple line. Okay, as you can see, it decreased to like 600 degrees C. All right. So now the question is, when we use a turbine engine, for example, right now we have cobalt. We use pure cobalt as the turbine material. And then it will oxide with oxygen to form cobalt oxide. And then with this environment, SO3, then it will form cobalt sulfate. And then it form like cobalt sulfate, and with sodium sulfate form this beta phase. That's the solid solution, right? Now the question is, if I want to use this material at 700 degrees C, okay? How stable is beta phase, all right? If beta phase is stable, then this material probably is safe, right? And what is the maximum SO3 partial pressure the beta phase can tolerate at this application temperature. So from this diagram, we cannot tell that, but if we plot this partial pressure of SO3 contour lines onto this diagram, then we can tell that the cross point at 700 and the melting temperature, the partial pressure of SO3 is 10 to minus 4.53. What does this mean? This means if in the environment, the partial pressure of SO3 is lower than this value, for example, is minus 5 or 6, then the beta solid solution is stable, okay? It's solid state. Then the material probably is okay. However, if the partial pressure in the environment is higher than this 4.53, then liquid will come out, which will make this material completely corroded, okay? So it will become liquid in the surface. Okay. So that's the binary, pseudo-binary system. However, let's say, what about we add some nickel to cobalt? And then how the tolerance of beta phase will be, okay? So in this case, for example, we add 20% of nickel in cobalt for this cobalt 80 nickel 20 alloy. Then we can calculate this highest tolerance of partial pressure increase a little bit, okay? But if you add more of nickel, let's say now we become a nickel alloy, nickel 80% and cobalt 20%, then the tolerance become even higher. So which means nickel is more corrosion resistant in this application. From this simulation, we know we have this idea for alloy design. We can add different components and to see how different components can improve the corrosion resistance for the marine application. All right. And the second example is corrosion of alloy in the salt-cooled molten salt reactor. So basically, in this example, we know that the protective layers of reactor component will tend to dissolve in fluoride salt, which will lead to continuous material attack and eventually the loss of structural integrity. So in this SEM image, you can tell this reaction layer, and also from this EDS mapping, you can see this diffusion affected layer. For example, if you focus on this red mapping, that's the manganese. So as you can see, in the diffusion layer, manganese depleted. Okay, so that's is the diffusion affected layer. And from diffusion simulation, basically we can use available experimental data to calibrate the flux and so on information, and then we can simulate the diffusion effect layer. So this is the first plot is for 100 hours, and the second one is for 200 hours. Then we can project it to like even higher number of hours, like 3,000 hours, and so on. Then we can project how long this reactor material can be used before the diffusion layer is too large, okay? So that's another application to use CALPHAD simulation tools to understand the corrosion behavior of material. So I know we have 5 minutes, so I want to leave a few minutes for the questions. This is basically the summary of my presentation. CALPHAD approach has gone beyond phase diagram and has become a very useful tools for ICME practitioner, alloy design and processing optimization. And then I want to show the last slides. I would like to acknowledge the support from Air Force Research Lab. And if you, I know the time is very short, so if you have any questions you cannot be answered today, then you can contact us by email or phone. And I think that's all. And thank you for your attention. Questions?
Awesome. Thank you very much, everybody. There are a couple questions. I know we don't have very much time, but one of the questions asked was, does PanDat software support Python? So I don't know if you can comment on that at all.
Yes. Well, yeah, that's yeah. We have tried to use Python as an interface to interface with PanDat software to get simulated results, and then user can use Python to continue to program with their applications. Yes, we can do that.
Okay. Another question came in about the lack of oxygen in some of the, I think the salt applications you had. How did you perform the oxidation there when there was no oxygen?
Yes, well, that's a very good question, because I know I don't have time to talk a lot of, about the thermodynamic database. So in order to predict the oxidation, then we need to develop the database to contain oxygen and also oxide in the system. Once we have that information, we can predict what oxide will become stable and different at different conditions. So then we can simulate the oxidation part.
Excellent. If and how do you handle any uncertainty for the alloys where all the ternaries are not available in the thermodynamic database?
Yeah, that's a very good question. For ternary system, if we do not have enough experimental data, sometimes we need to do some like ab initio calculation, first principle calculation, to see to get some you know ballpark about the energy at different area, different composition. Then we can use that information to develop the database for the ternary system that has no enough information. Certainly, we sometimes we need some experimental data to validate.
Thank you very much. And can people reach out to you directly if they if they would like a copy of this presentation? I know we are obviously going to record it and post on the LIFT website, but I would encourage folks to reach out to you directly with any further questions, or if you would like copies of the slides. I know one of the participants would like a copy of the presentation because they have Python with PanDat at their company. So can they reach out to you directly to do that?
Yeah, sure. Any questions, just send us an email at info@CompuTherm.com. I will certainly address any questions you would like to ask.
Awesome. Well, thank you very much for that. Be sure to reach out to CompuTherm via the email address, the phone number, and the website on your screen. And thank you very much for participating today. Stay tuned next month as we host another webinar from LIFT. And until then, we appreciate your participation, and thank you very much. And thank you, Dr. Fang, for your presentation today. Or Dr. Zhang for our presentation today, and thank you very much everyone for participating. Have a great rest of the day.
All right, thank you.